Okay, class, I'm going to call this Lesson 11, Lecture 9, which is going to cover the Lecture 9 uh, PowerPoint slides, which basically are on binomial expansion, sometimes called the binomial coefficient, and then the chi-square test. And this is going to be the last uh, lecture PowerPoint series for exam one. So after this, then we'll start into material for exam two. So everything that's going to be covered on exam one will have been covered when we finish this particular lesson 11. So when you're a geneticist, it's super important that you understand probability and statistics because in nature, just like in real life, things don't always occur exactly as you would expect. So we could just take something like a coin toss, for example. And let's say that you're tossing a coin, you're just at home and you're tossing it 10 times. So your expectation would be that when you toss that coin 10 times, that half the time it would come up heads and half the time it would come up tails. So it should be 5 heads and 5 tails. But that might not necessarily be the case. And you could try this at home. So flip a coin 10 times and see how often it comes up 5 and 5. And it's probably not very often. So now you have to ask yourself, well, how odd is it if it comes up 6 heads and 4 tails? Or how odd is it that it comes up 7 heads or 3 tails? Or how odd is it that it would come up 10 heads and 0 tails? And you probably logically in your head know that statistically it would be much odder to come up 10 times heads and no times tails than, say, 7 times. And that would be more unlikely than 6 times. And the closer you get to 5 is more in line with what you expect. And you have to be able to draw a line in the sand and decide, when do I think that there's something wrong with this coin? Maybe it's weighted. And casinos do this all the time. So I don't know if you know this or not, but Ben Affleck was tossed out of the Hard Rock Casino for counting cards. Now, how did they know he was counting cards? Could they read his mind? No. They were simply looking at probability and statistics, which is exactly what we're going to look at for genetics, except they're more concerned whether or not he is beating what they think the probability is. So in real life, if you're playing blackjack and you sat down and played with a friend, just like a standard dealer game at a casino, the dealer should win 51% of the time and the player should win 49% of the time. So the house always has the odds. However, if you learn how to count cards in a simple numbering system, then you can change that probability in statistics because you know how many cards have come out that are big cards and how many cards that have come out that are small cards and how many cards are left in that shoe that dealer is dealing out. And so in the end, you can, because the odds are so small in favor of the house on that particular game, you can turn those odds in your favor and win almost every time. Now, you're not going to win all the time. Sometimes you're going to lose, but there's numerous specials that have been shown on, the MIT group that was counting cards. And in the end, you're going to beat the house, and they don't like that. And so they did the same thing with Ben Affleck. They were watching him. They have been watching him. He plays all the time there. And they had just had enough. They knew that he was counting cards. They can't prove it, but they know that if he statistically plays long enough, so for example, if you were flipping coins 100 times and 100 times it came up heads, you would be like, really, what's going on? So we have to figure out statistical methods in genetics because we might want to track the segregation of genotypes or phenotypes. we want to be able to predict the outcomes or the probabilities of outcomes for inheritance. Are you going to get that breast cancer gene or not? And what's the probability if you get it that you're going to get breast cancer? Um, or we might want to calculate specific probabilities, like, you know, if how many chickens should I expect to have large eggs when I breed these two chickens that have large eggs? Or, maybe we just want to find out how likely it is that, it's two genes in one, or two alleles in one gene system, um, that we got a 1 to 2 to 1 ratio. And maybe, so that would be 25%, 50%, 25%. Maybe we got 20%, 58%, and 18%. Is that in line with what we thought? When do you call your friend a cheater if, let's say, you're betting on coin tosses and you're betting $100 a toss and they win 6 times? So let's say they bet heads and it came up heads 6 times. Are they cheating? If you do 10 tosses, maybe not. Well, what about 7 times? Are they cheating? Well, then you might be a little suspicious. 8 times? 10 times, you might be very suspicious. And maybe that coin is weighted, or, same thing with dice and craps or whatever. So I love this subject. I'm super passionate about it. A lot of genetic students just absolutely hate it and don't get it. And sometimes you just have an epiphany and you're like, okay, that makes sense. So I'm going to try to make this as simple as possible so that you can understand how we can predict the outcomes of different things. All right. So let me move this thing down again. It's always in the way. All right. Here we go. Okay. So let's say we have events, right? And just to let you know that there are events that are independent of one another. So if you ever go to a casino, and you go to a roulette table, they're going to have a big sign probably that you can see all over the casino, and it's going to tell you how many times that roulette wheel has hit black and how many times that roulette wheel has hit red. And so why do they do that? So the reason they do that is that they want to encourage you to come and bet. Let's say that it's hit black 7 straight times. Well, you might think, okay, the probability is that it's going to hit black again. Or maybe you might think, oh, the probability is it's going to hit red because it hasn't hit red in a very long time. So red is due. And so they psychologically encourage you to make those bets. But in the end, it doesn't matter. It wouldn't matter if it rolled 100 blacks before you placed your bet, because every time they spin that wheel and throw that ball through it, it's an independent event. So what's the probability? And let's just ignore the green spaces because that gives the house the advantage. But let's just say that it's straight up black or red, like a coin toss, heads or tails. What's the probability, even though it was 100 times black before, we spin that wheel and it comes up black again? Well, it's 50-50. It doesn't matter how many times it came up black or red or anything that happened in the past. It's a mutually exclusive event. It's the same thing as kids. If you had 7 boys, and I talked a little bit about the Y chromosome is lighter, so the probability of having a boy is about 51% versus a girl, which is 49%. But let's just say it's even for fun to prove a point. So there is a 50% chance you have a boy, 50% chance you have a girl. So let's say you had 10 girls. What's the chance your next kid is going to be a girl? 50-50. Or a boy? 50-50. It does not matter what happens before. So every event is equally likely as long as they're mutually exclusive from one another. They're not tied together. All right. And in the end, when we add up all these probabilities, they have to be 100%. So, like if we flip a coin, the probability is that it's going to be a heads is 50%, one half, then the probability that it's going to be tails is also one half. And so taken together, one half plus one half equals one, or 100%. And it's the same thing with rolling dice. All right. So just to reinforce this, independent events are events that one outcome does not affect the other outcome. They're both equally likely. So if I tossed a coin 2 times, right, then the probability that them coming up heads both times is one half times one half, because they're exclusive of each other. The universe doesn't care that tails was flipped first or heads was flipped first, right? The next flip has no influence on the previous flip, and the flip after that isn't going to have any influence, and so on and so forth. So if they're independent events, we can multiply them again together, like I said. So if we have one event where, so let's say we have one event and we flip a coin, what's the probability it's going to be heads? Well, that's one half, right? And tails is also one half. So what's the probability I flip the coin twice and it comes up heads both times? Well, we can use the rule of multiplication to predict that outcome, which is 1/4, right? We could do that for dice. So what's the probability that I'm going to roll snake eyes? And so this dice does have no influence on this dice. So if I roll these at the exact same time, it doesn't matter. How many ways can I get a 1? Well, there's only 6 sides on a dice, so it's 1/6. And then I have to get a 1 on the other dice, so that probability is also 1/6. And according to the multiplication rule, the probabilities, I can multiply independent events together to get my probability. So the probability for me to roll snake eyes on a craps table or just rolling 2 dice is 1 out of 36. And so that it wouldn't matter how many dice I roll or how many times I flip the coin. If I flip the coin 3 times, it's 1/2 times 1/2 times 1/2 is 1/8. So the probability of me flipping this coin 3 times and it coming up heads every time is 1/2 times 1/2 times 1/2, which would be 1/8, right? And if I did it again, it would be 1/16, and so on and so forth. Okay, so let's apply this to some sort of genetics rules. So what's the probability that if we cross this black guinea pig with a white guinea pig, that any single offspring from this F1 cross, right, where they're both black, is gonna be black, right? So, I mean, this is pretty simple, and you probably already know this. But this cross, right? The probability from this cross, this guinea pig can only give a big A. This guinea pig can only give a little a. So any offspring out of that is going to be big A and little a. There's no variation here. There's no way that this could change, unless we had crossing over that occurs in, prophase 1 of meiosis. But for the most part, we're going to just ignore that for now. It's going to get complicated later, but for right now, we're not going to throw in any crossing over or synapses or anything like that. And so our probability is 100%. 4 out of 4 of guinea pigs, and if we did the Punnett square, right? 4 out of 4 of these guinea pigs are going to be big A, little a, they're going to be heterozygous. And so if we mate them together, we know that those are 2 heterozygous. So what's the probability that we're going to get either big A, or big A, little a? Well, we know from doing Punnett squares, a bunch of these things, that the probability here is, this is a little a. big A, big A, big A, little a, big A, little a, little a, little a. And we know this from Mendel's rule. It's a 3-to-1 ratio. So we would expect 3/4 of these offspring to be black and 1/4 of these offspring to be white. So the probability is 3 out of 4. And we know this. It's nothing surprising. So what's the probability that they would be white? And we just did that problem, so it's 1/4. No big deal, right? So now we're gonna say what's the probability that these two parents, right? So this is the monohybrid cross. We know if this is one gene and two alleles, that we're gonna get a 3-to-1 ratio if it's following Mendel's rules. Not that there's two genes involved or multiple genes involved or pleiotropy involved or any, independent, incomplete dominance or incomplete dominance or codominance. Nothing like that. Just straight up Mendel rules. And so we can, just like the coins, we can multiply the probabilities together. So what's the probability that the first offspring is black and the next two are white? Well, this is an independent event, right? 3/4 of the time they're going to have a black offspring, right? So first offspring is black. Probability is 3/4. Next offspring is white. That probability is 1/4. Then the one after that is also white, and that probability is 1/4. So we just multiply them together. 3 times 1 times 1 is 3. 4 times 4 times 4 is 64. So the probability is 3 out of 64. And if you're doing this on the test or whatever, you could simply, divide 3 by 64. And let's see what I get. Calculator here. I get 4.7%. So 0.0468. So 0.046875 is the actual number. And of course, we can round this. So I would call this 0.05, which is roughly 5% probability that this would occur, right? If I'm rounding this up, right? So remember, these are independent events. That no event that previously occurred has any bearing on any event after that. And so let's change this up a little bit and say, what's the probability of any one offspring is black and the other two are white? So this is different than this question, right? This says this is an exact order. These are independent events. Number 1 has to be black, right? There's no other option. Number 2 has to be white. Number 3 has to be white. These are all independent events from one another. Now, this question is asking something completely different. 1 is black and 2 are white. Now, there's multiple ways that this could happen. We could have a black guinea pig first and then 2 white ones. We could have a white one and then a black one and then a white one. Or we could have 2 white ones and a black one, right? And so we have to add rule of addition. Says we have to add all these probabilities together to get our probability outcome. So in this case, we have 3/64. We already calculated that from the previous slide, plus 3/64, right? Because it could occur this way, and then plus 3/64, which could occur this way. And so the rule of addition says, because these are not exclusive, they're not independent events of one another, right? A way to rephrase this is that if it is ordered, right, like black, white, or so on, then you cannot use this technique, this rule of addition, to figure out the probability. If it's a complete order, then you use the rule of multiplication to calculate that probability. And then we can add them together. So again, we can go back to dice. And so let's say that we have a dice. So let's say, what's the probability that we're going to roll a 7? So this doesn't say that there's any particular order that could occur in, and then that means that the dice aren't independent of each other. Just like the two, there's only one way to get a two, but there's multiple ways to get a seven on dice. You could get a one and a six. Two, three, four, five. What is going on with my tablet? It is not like my hand on it. Okay, so we could get a one or a six. You know what? I'm just gonna pull up a probability sheet for this. Okay, I just looked up dice probability so that I didn't have to draw out every single dice. And you can see this is much easier. So remember when we roll dice, right? The odds of getting any one of these numbers is 1 out of 6 because the dice have 6 sides to them, right? And so if we're rolling two dice, they're independent of one another. One dice doesn't care if I roll a 1, 2, 3, 4, 5, or 6. It's all independent of whatever that first die roll is. And so we can multiply them together. So any probability of any one of these dice landing in the way it shows on this table is 1 out of 36. And that's just like a Punnett square. So we have 6 by 6 grid. It's 36 outcomes. And that's the rule of multiplication. But because this outcome right here, which is 2 on this dice and 1 on this dice, is the same as 2 on this dice and 1 on this dice, there's 2 different ways to get a 3. So we can add those together. And so we have 136 plus 136, which is 236. There are 3 ways to get a 4, 4 ways to get a 5, 5 ways to get a 6, and then 6 ways to get a 7, right? We could get a 6 and a 1, 5 and a 2, 3 and a 4, and then we could go the other way. 4, 3, 5, 2, 6, and 1. And so we have to include all those possible outcomes here. And so the chances of this is 136. This is 136, 136, 136. And so we have 636 or 1/6 probability of rolling a 7, which is the highest probability of all dice rolls. And then, 2, 11, and 12 is the lowest one. And so that's craps. And then this is the winning or losing rolling hand. So that's what we're talking about when we talk about this rule of multiplication and rule of addition. All right, so hopefully everyone understands that. Okay, so if we have these different events that we can add together, right? It's not a straight order, so we can't just multiply it together. We can use a binomial distribution to help solve this problem without having to do a whole bunch of like Punnett square like calculations like I just showed you for the dice. Okay, so when we do this, hang on a second. I'm just gonna pause this because I don't know what's going on. Okay, so I think the janitor's here. I'm in my office. It's kind of late, so if they come in and interrupt me, you'll know who it is. And if I get killed, it's not the janitor. It is 7:55 p.m. and on a Tuesday, the 20th of February. Okay, so so we have a probability, and we want to know the chances of having, of 6 kids that we have. 4 of those kids are going to be boys, and 2 of those kids are going to be girls. So you know that we could do this out, right? And we can figure out how many ways that we could have boys and girls. So we could have a boy, girl, boy, girl, boy, or boy, girl, or girl, boy, or and so we could go through all the different possible combinations. In genetics, this can get really complex really quickly, so it's easy to have a shortcut method here. And so the shortcut method is this binomial equation. The binomial equation simply says that or it's also called binomial expansion. So it simply says that we're going to let n equal the number of events. right? And so those number of events, in this case, if we're talking about 4 boys and 2 girls in any order, right? I mean, if it was like 4 boys and then 2 girls, then it would be simple. It would be 1/2 times 1/2 times 1/2, right? Because there's 50-50 chance of having boys or girls, times 1/2 times 1/2 times 1/2, right? And in the end, we get 2 times 2 is 4 times 8, 16, 32, 64. So the probability of having this would be 1 out of 64, right? But that would be 4 boys. So boy, 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 girl, girl, right? And that's an ordered event, right? And that uses the rule of multiplication. But this isn't, I'm not asking this question. What I'm asking you is what's the odds of having 4 boys and 2 girls in any order? And to do that, we use the binomial. So how many events are there? Well, there's 6 because we're going to have 6 kids, right? So we're going to let n equal 6. And so we're same thing here, right? So we can use n offspring. In this case, like if the guinea pigs, we're talking about 3. Here we're talking about 6. What's the probability that K have a certain phenotype, right? So, and the rest do not. So we have in the previous problem, and so I'm just going to ignore the kids problem for right now. We'll come back to that, but let's go back to the guinea pig one where we had like the 3 guinea pigs, and we said we had what was it? Let me back up. So we have 1 black and 2 white in any order, right? So 1 black guinea pig, 2 white guinea pigs, any order, right? So we could have black, white, 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 black, or white, black, white. So anyway, so that's how many offspring? 3 guinea pigs. What's the probability that K have a certain phenotype? So we could let this equal whatever we want. We could say K equals black, right? So K is black. And so the rest have N minus K, right? Which is not black, right? So in this case, we define that it's only going to be 1 black offspring. And so the ones that are not black are going to be N minus K. In this case, so N equals 3 offspring, K equals 1, because we define that as black, and then the ones that are not black are going to be N minus K, right? 3 minus 1, which is going to be 2, right? Which we already know. So we don't really have to calculate that out. All right. So in order to solve this kind of problem, we have to answer 2 questions. The question is, how many ways are there to get that specified family? Just like how many ways can we get the dice? How many ways can we get a 7? How many ways are there to get N offspring, K of which have a certain trait, in which K do not have a certain trait? What's the probability in each family? And so we can multiply this answer by this answer to get our outcome, right? First, we want to know how many different ways we can get that, and we already calculated that, right? So, we showed that. There's 3 ways to get one black and 2 white, right? And then for this one, what's the probability of having N offspring, 3 offspring, which with a certain trait, right? So we've already calculated this. We said that to get the 3 offspring, right, for each phenotype, we know that in order to get a black one, the probability is 3/4, and to get the white ones, it's 1/4 and 1/4. So we just have to figure out what the probability is to have this, right, in that particular order, and then we have to add it together for the ways that we're going to get it. So this is the easier way to do that. We just plug it into the binomial. So we have n factorial divided by k factorial, and then n minus k factorial. So if we're doing our guinea pig example, n equals 3, right? We had 3 offspring. So 3 factorial. If you don't know what a factorial is, it's 1 times 2 times 3. So that's 3 factorial. If it was 4 factorial, it would be 1 times 2 times 3 times 4. If it was 5 factorial, 1 times 2 times 3 times 4 times 5, and so on. And there's probably a factorial in your calculator that does that calculation for you. And you certainly can use this on the test. You could do it long ways, or you could use the factorial function on your calculator. I could care less. Or could not care less is like my wife likes to correct me saying. Okay, so anyway, we have 3 factorial, so we know that 1 times 2 times 3 is 6. So on the top, we're going to put a 6, right? And then k, right? So in this case, we define k as being one outcome. In that case, it's black, so we have 1 factorial. And then we're going to multiply that by the other possible outcome, which is, in this case, white, right? Not black. So that would be n minus k factorial. So n is 3. K is 1, so 3 minus 1 is 2 factorial. And so 1 factorial is 1 times 1, which is 1. And then 2 factorial is 1 times 2, which is 2. And we multiply those together, we get 2. So 6, right, from our 3 factorial. So here's the formula. 3 factorial, right, which is n, divided by 1 factorial times n minus k factorial, which we calculated as 2 factorial. And if we do this out, 1 times 2 times 3 is 6, and 1 times 1 is 1, and 1 times 2 is 2. So that total is 2. So 6 divided by 2 equals 3. So our answer is 3, right? So there's 3 ways. This is calculating how many ways that we can get this. We're not done because we have to multiply it by our probability, right? Our independent event probability. And to do that, we can simply take the probability the offspring has this trait, whatever that trait is, to the k power, and then the probability of the offspring does not have the trait, which is to the n minus k power. So for our guinea pig example, remember, n equals 3, k equals 1, n minus k equal 3 minus 1 equals 2. All right, so we know all these values. So the probability the guinea pig is black is 3/4, right? We know that from Mendel's rule, it's 3-to-1 ratio. And then we just raise it to the k power. In this case, it's 1, but it could be anything. And so we need to multiply that by the probability that it's not black. So we know the probability that it's going to be white is 1/4. And how many times is that going to come up? Twice. We showed this in a very long way. But anyway, so we just multiply 3/4 to the first power, which is 3/4 times 1, which is 3/4. So we get 3/4, and then 1/4 to the second power is 1/4 times 1/4, which is 1/16, right? So we multiply 3/4 by 1/16, and then we get 3/64, right? And now we have to multiply that by 3, which is the value we got from the factorial, the binomial, right? Which is right here. This is our 3 value from the binomial. So that's part A. We got 3 for this value. And then part B, we got 3/4 times 1/4 times 1/4, which is 3/64. And then remember, we just multiply those together. So 3 times 3/64 equals 9/64. Right? Which is, so we got 3 here. We got 3/64 here. So we multiply them together and we get 3 times 3/64, which is 9/64. Right. So that's how you would calculate the probability that you would have a black and 2 white guinea pigs from this monohybrid cross. Okay, so let's do another one. I started off talking about the kids, right? And so we know that it's n factorial divided by k factorial, right? Remember, that's whatever the outcome is. And then we have n minus k factorial. And then, so we have to multiply that by the probability, which is, our first probability that of, k. So, how many outcomes that is, times the probability of, and we'll just say that this is q. And then again, that would be n minus k of it, right? Then this is what the whole formula looks like to figure out what the factorial is. So let's go back to the question. 4 boys and 2 girls, any order. So let's try to solve for this. So how many outcomes are there? Well, there are 6, right? Because we have 4 boys and 2 girls. That's 6 children. So n equals 6. So we can do the 6 factorial, 1 times 2 times 3 times 4 times 5 times 6, right? And so if we do that, let's see, what value do I get? Well, let's just write it out, and then we'll figure out the factorial values later. I can plug it into a calculator. I can multiply it out, so I'm not wasting a bunch of time. All right, so we have n factorial, right? Whatever that is, n factorial divided by. And so in this case, we would have the number of events, and we decided that this is 6, and then we're going to divide it by k, right? We can make it this, the boys or girls, because it won't matter, right? If you do 4 boys, right, and then that'll be 4 factorial, and then we would have so that would k. So in this instance, k would be 4. So n minus k factorial would be 2, right? So basically, we're just saying 2 girls. So we're doing 4 factorial for boys and 2 factorial for girls. And then we have 6 factorial on top of that. And so this is going to give us our potential outcomes here. That's how many ways that we can get boys or girls. All right. And so let's just calculate it out. I'm going to pause this and then I'll do the math and I'll come right back. Okay. So I did the math. 6 factorial is 720. And then 4 factorial is 24. And 2 factorial is 2. So 24 times 2 is 48. And then if you divide 720 by 48, you get 15. So what that means is, and you could test this out if you want to, there are 15 different ways to get 4 boys and 2 girls in any order. And go ahead and write it out if you feel like it, but that's the value. All right, so we know how many different combinations we have. And now the orders are set, right? There's 15 distinct orders. So now we multiply it by that probability, right? So we have the probability of k, right? So the probability, in this case, we made k equal boys. So the probability of boys is 1/2, right? You've had a 50-50 chance of having a boy. And we have to raise that to the power of the number of outcomes of of boys that we have, right? If it was this straight order, it would be 1/2 times 1/2 times 1/2 times 1/2, which would be the chances of us having 4 boys in a row, right? And that's simply what this is. So this probability of K, right, is 1/2, and then so the probability of not K, right, n minus K is girls. And so the probability of having a girl, we could say that this is n minus K probability, without trying to get confusing, right? So this is girls, probability of having a girl, uh, probability of having boys. So probability of having 4 boys in a row, and then this one is 2 girls in a row is 1/2. Right, that's the probability, and then we have to raise it to the n minus k power, which is 4. So n is 6, and k is 4. So 6 minus 4 is 2. So we raise it to the second power. So that's girls, right? 1/2 times 1/2. So in the end, it's 1/2 to the 6th power, which is 1/64th, right? And so if we multiply this out, we should get 15/64 probability of getting 4 boys and 2 girls. And so I'm going to pause this and I'll just do this as a decimal form. Okay, so I did the math, and 15/64 reduces to 0.2343, which is 23.43%. So that is the probability of us having 4 boys and 2 girls in any order, right? If it's ordered, then we can't use the binomial, because the binomial is telling us how many different outcomes we can have that are the same. Right? Just like the rolling of the dice. And hopefully that makes sense. Okay. All right. So there are some quiz questions, and of course, I put some practice problems on your problem set as well, so that you can practice figuring this out. All right. Okay. So this should be review. If you want to find or you want to know the steps into identifying a single gene, like for example our pea flower gene, that affects a trait. In this case, it's the flower color. So figure out what you want to study. If is it the flower color, is it the Drosophila eye shape, color, whatever. And then of course you're going to find mutants that affects this trait, or you can introduce mutants that we talked about how to do that. And then you cross the mutant with the wild type to create an F1. So in this case, generally we're going for a heterozygote, right? In the F1 generation, and then we self them, so we end up with a monohybrid cross. And then when we do that intercross, that monohybrid cross, sib mating, so you're guaranteed that all of them are going to be heterozygous in this case, right? Because you're going to have a normal times a mutant, and all of the offspring in the F1. This is the parental generation. This is the F1 generation. All those should be heterozygous. If you mate them to themselves, they're all heterozygous. So brothers and sisters all have the same genotype. And when you intercross them, you're going to get an F2, and from doing all these crosses that we're going to get a 1 to 2 to 1 genotype ratio. 1 to 2 to 1, which is 1/2 to 1/4 to 2/4 to 1/4. And a phenotypic ratio in this case would be, wild type, whatever that might be. Purple in the case of flowers, red eyes, normal shape, and Drosophila. That's going to be 3/4, and then the mutant phenotype will be 1/4, right? Our 3 to 1, our typical 3 to 1 Mendelian ratio, right? And so if we don't get a 3-to-1 ratio, right? Maybe it's off a little bit, and I threw an example and then a problem set for you guys for the first problem set, and a lot of people were like, "Well, that's not exactly 3-to-1." Well, I'm sorry, that's how life is, like flipping the coin. It's not always going to come up 5 times heads and 5 times tails. So how do you know if if that is within your expectations? And this could be really important if you're trying to tell somebody what the probability is their kid's going to have uh, non-Hodgkin's lymphoma, or the probability that they're going to have Huntington's disease, or if they're going to have Parkinson's or any other genetically related disease, breast cancer. You need to be pretty good at predicting the outcomes, and knowing if that gene is following Mendelian ratios or if it's off, like in epistasis or in, you know, codominance or an incomplete dominance or anything like that. So we're going to look and make sure, and this is used in things to figure out like if drugs are going to be useful, or if we should throw Ben Affleck out of the casino. All right. So we talked about this. This is nothing new. You can get all kinds of variation and outcomes, like we talked about with the coin toss. Um, and so we need to examine if what we observe is what we expect. So to do that, we can do something called a chi-square analysis. And this is what they did to figure out if Ben Affleck was cheating or not. And this is what I would do if I was flipping coins with my friends and they kept beating me or rolling dice or what have you, to try to figure out, is this what I expect, or is there some cheating or something weird going on, right? Like, is this in line with what we expect from Mendel, or is this something weird like epistasis, or is it polygenic? Or is it, environment? Or is it something else, right? We want to know, is this in line with what we expect, or is there something funky going on? Is my friend being honest, or are they cheating? So let's say that we're looking at a certain phenotype from mutation in a single gene, right? This is nothing new. We did flowers and we've done pea shapes and pea colors and what have you. So let's just say wild type is green and a mutant is a purple leaf. So we cross them. We would expect this one to be, well, let's follow Mendelian nomenclature. So the dominant would be green, so we could be big G, and this would be little g. In Drosophila, it's completely different. We talked about that. And then here, we would expect all the offspring to be heterozygous for that particular trait. And then if they selfed, we know that we would expect a 3-to-1 ratio, right? So let's say we counted these plants, and 71 of these plants were green and 29 of these plants were purple. Well, is this in line with what you expect? How do you know if this is following Mendel's rules or if it's following something else? And so to do that, we have to perform a chi-square analysis. So the chi-square test is basically telling you if what you observe is what you expect, right? And so let's do something simple that I do with my intro bio class when I teach them chi-square analysis. And so one of the things I do is I'm like, okay, well, let's just take the coin toss, for example. So we have heads. This is so simple, and tails, right? And so we know that the outcome is 50% heads and 50% tails. So we need to figure out a number. How many times are we going to flip this coin? Let's just say we're going to flip it 10 times. So our N is 10. Well, of this, we would expect 50%, right? Or 10 times 1/2, which is 5 times should be heads. And so this is our expected. And in this case, we would also expect 5 tails, right? So Of the 10 coin tosses, again, 1/2 would be tails. And so 10 times 1/2 it would be 5. 10 over 2 is 5. So this is what we would expect, right? And let's say are observed. All right, so you're betting your friend $100 a coin toss. You take tails, and it comes up 4 times tails, and it comes up 6 times heads. Right. So this is a little different than what we expected, but are you ready to, take your friend in the back alley and rough them up over that like they did, Vegas gangster style back in the day? Or is it this just due to natural variations in probability and statistics? To figure that out, we can use the chi-square, right? So chi-square is super easy. You just got to remember the formula. So it's observe minus the expected squared, that's where the square comes from, over the expected. And you have to do this for each outcome, right? So we have to do one of the chi-squares for heads and one of the chi-squares for tails. So let's move it over here. So let's do chi-square for tails first. So our observed, right? Our observed tails is 4. Like we flipped 4 tails out of our 10 things. What we expected was 5 tails. So 4 minus 5 equals -1, and we have to square that, right? This is a squared value. So -1 squared is a negative times a negative is a positive. So we have a 1. And then we divide that by our expected. So our expected is 5. So this is 1/5, right? Or 20.20, right? And then we also have to do the same for heads. So for heads, we would do our observed is 6 heads. We subtract that from our expected, which is 5. Again, squared. So this is 1 squared, which is 1. And then we divided that by our expected, which is also 5. So this is 1/5, which is also 0.2. And then we add the values together. So this would be 1/5 plus 1/5, which is 2/5, or 0.2 times plus 0.2, which is 0.4. All right, so this is our total chi-square value for this outcome, right? Now, what we're trying to figure out is the area under a curve. You guys, if you're students, you constantly probably ask your professors to grade on a curve. But do you really know what the curve is? And so the curve is what we would statistically expect a student to do in a class. Like, what's the average? And so I'll ask you straight now, what is the average grade that you would expect a student to get in any college or high school class? And hopefully you said C, because if you look on your report card or whatever, it says C equals average. Now, what is a C? Well, if you've gone to school long enough and you're in college right now, you should know that to get a C, it's 70 to 80 or 79%, right? So right in the middle of that would be 75. So in any college class, we would expect most people would be average, right? Like if we looked at height or whatever, the average height for males, I think, is 5'8", maybe it's 5'9". It depends on what country you're at, right? But it would be really a real big outlier. It would be really weird to have someone that's 7 feet tall or 7.5 feet tall. And it would be really a real strong outlier in the United States to find someone that's 3 feet tall. So most people would be right in the middle, just like that. And you're going to have some people that in the class that's going to study like crazy, and maybe they already know genetics or they're like a savant, and they're going to get 100%. It happens every semester. And there's going to be some people that their house blows over, their dog runs away, whatever, life happens, and they're going to not get so good of grades, and maybe they don't study at all, they don't have time, or maybe they just gave up on genetics, and so they're not going to do anything. I've had have students right now not turning in any work, so they're going to get they're going to get like 20%, maybe even lower. Maybe they'll get a 5%. I don't know. And this is going to change if people drop the class. But you would expect the bell curve, it's going to be real small down here. It's going to get bigger towards the average, which is the 75%. And then it's going to get smaller as we go towards 100%. Right? And so that's the curve. Right? And when I give an exam, I make up new exams. So if I took the exam, I would get 100% on it every time. So I'm not a very good predictor of what the average score in the class is going to be. And there's no way I can do that unless I went around to a bunch of genetics students that took my class, and gave them a practice test and figured out what the score is. So that's why professors usually grade on a curve. We generally make the test a little bit harder. And that's because we can always push it back to this average, right? Students really hate it. Let me pause this, and I'm running out of battery. Okay, so I'm back in business. So anyway, students really hate it if you are taking away points from their exam. And so we don't want to push the curve this way. We always want to push it this way. And that's why tests generally are harder. Especially in genetics, than they are easier, because it's more appropriate for me to push the curve to up and give you points than take points away. But that's how it works, right? And so when we're doing chi-square, we want to find out what the area is under the curve that's going to be normal, right? Something that we would expect, not these weird outliers of people, getting 100% or not doing any work when they paid for the class. So unless you're a big fan of calculating areas under curves, which you need calculus to do, then because this area only changes based on the number of outcomes, and we call that the degrees of freedom, then we can use a table because the area doesn't change. The only thing that changes is the degrees of freedom, and that changes the area under the curve, so we just use different numbers for that. So I'll show you. Let's go back to our example here. All right, so 71. We have 71 wild type and 29 mutant plants, so 71 and 29. We have to add those together. That should add up to 100 because that makes it easy, right? So 71 plus 29 is 100 total. And so we have to calculate, what do we expect here? If it's following straight up Mendel rules, we would expect 75 of these to be wild type. And how I calculated that? Well, we have 100 plants, and we would expect, based on Mendel, remember 3-to-1 ratio, times 3/4 is 75. And then we have 100 plants, and then purple would be 1/4, right? Remember 3-to-1 ratio. And so that would be 25, would be, our mutants. So this is our expected, 75 and 25 plants. And our observed was, so our expected, this is remember we have to do it for each one. So, sorry, that's not purple, that's green. Green, and this is purple. And so our observed is 71 green and 29 purple. Is that in line with Mendelian ratio? Well, let's do a chi-square. So do chi-square is observed minus the expected squared over the expected. And remember, we have to do it for green, and we also have to do it for purple. And before we do this, let's just go ahead and calculate our degrees of freedom. So degrees of freedom is super easy. Degrees of freedom is the number of outcomes minus 1. So in this case, this plant is either green or purple. There's only 2 outcomes. So 2 minus 1 is 1. That's how many degrees of freedom we have here. If we were flipping a coin, we would have 1 degree of freedom, right? Because it's either heads or tails. So 2 outcomes minus 1 is 1. If we're rolling dice, then there's 6 outcomes, right? It could be a 1, 2, 3, 4, 5, or 6. So 6 outcomes minus 1 would be 5 degrees of freedom. And that's how we figure out where we look up on the table to find that area under the curve. Okay, so let's do green. We observed 71 green flower leaves, and we expected 75. So 71 minus 75 is -4. And if we square that, that's going to give us 4 times 4 is a positive 16. And then we just divide it by our expected, which is 75. So 16 divided by 75 would be for green. And then let's do our purple one. So chi-square for purple. This is for green. So we do observe minus expected squared over expected. And here we have observed is 29 purple. And expected is 25. So again, we have 4 squared, which is 16. And then our expected here is different. So in this case, we're dividing this by 25 and not 75. So let me do the math real quick, and I'll be right back. Okay, so I did the math. So 16 divided by 75 is 0.213 repeating. 213 is fine. 21 is fine. And then 16 divided by 25 is 0.64. So remember, we add those together. We have to add the chi-square for the green and the purple. So we get 0.213 plus 0.064, and that gives us 0.853. And so that is our chi-square value. You could round this, right? Like you could say this is 0.21, and you might end up with 0.85, and that's okay. That, unless it's relatively close to your critical value, which is your cutoff value, the area under the curve that we're going to use instead of doing calculus, we'll use a table for. Whatever that value is, if it's not crazy close, then a little bit of rounding won't matter. All right. So what's going on here? Okay, so I rounded this off to 0.85, and that's fine. All right, so that's our chi-square value. We talked about the distribution and all that other stuff. So in most cases, whenever you're doing science, you have a 5% critical value. So, and then we talked about the degrees of freedom, right? It's whatever the outcome is minus 1. So in this case, our degrees of freedom is 2. 2 outcomes, either purple or green, minus 1 is 1 degree of freedom. And so our critical value, the value that is going to be anything below this. So if anything below that is in line with what we expect, with our expectation. So that means Ben Affleck can say and play in the casino, our friend isn't cheating. This is in line with what we would expect for Mendelian ratios, right? If our chi-square, so if our calculated chi-square is above our critical value at 5%, this is the cutoff that scientists use. So, there are going to be some outliers, right? But for the most part, this is good enough, So if our chi-square value is above our critical value, in this case, if it's bigger than 3.841, then something weird is going on. It's not in line. We reject our hypothesis that it's, follows Mendel's rules or whatever. So we reject the null hypothesis. Right? And here we would accept the null hypothesis. Right? And so since our value is 0.85, which we calculated, and our critical value is 3.841, this number is smaller, and so therefore it's below our critical value. Our chi-square value is below our critical value. then it's in line with, so we would accept our null hypothesis, and we would say, yes, it is in line with what we would expect our 3-to-1 straight up Mendelian vanilla genetics outcome. So hopefully that makes sense. And then this is basically just doing the same thing. So we reject the hypothesis if it's bigger than the critical value, and if it isn't, then we accept it. We don't reject it. So in summary, we have confidence that purple leaf color results from a recessive mutation on a single gene, right? Just in line with Mendel. So these are the steps that we just went over. I'm not going to waste time going over them again, but you can do the chi-square test on anything. I use this quite a bit in science to test whatever I expect to be the outcome and what I observe to be the outcome. And then just remember, we talked about the rule of segregation, right? Which means that genes segregate into gametes, and then independent assortment means that they assort independently from one another. So it's kind of like the coin toss, right? What we're saying is that the gene for P color is on a different chromosome than the gene for P shape, and so they're going to assort independent of one another. That's not always the case, but when Mendel wrote his paper, all of the traits that he looked at were independent of one another. Now, statistically, that's super impossible. He probably made some data up, which you shouldn't do, but it went to explain his paper a lot more, or he could have gotten really lucky and picked all of these traits that just happen to be on different chromosomes. And as we go forward, we're going to talk about instances where we don't have this independent assortment, where genes are on the same chromosome and they travel together. So we call that linked. Anyway, so that's what the independent assortment, Mendel's law of independent assortment, and Mendel's law of segregation is. And remember, these things can line up, these chromosomes line up on the metaphase plate. So I just want to remind you, right? We have so we can have any outcome here. Let's say that I'm just going to use green for dad. Let's say dad's chromosome, this is number 1. So this is dad, this is mom, right? We know that they're going to have similar genes on them and similar locus. And then I'll say that this is number 2, and I'll stick with the way that we number stuff. So this will be a smaller, shorter chromosome. And then we have one from dad, which is going to be the same. They're homologous, right? So it can line up this way. And then if we have, this, rules of segregation, the independent assortment, show by the way that these line up, these homologous chromosomes line up on the metaphase plate. So when these segregate, we'll have a gamete that has all of dad's traits, the one that this individual got from their father, right? So let's just say that this is a male, and these are the traits it got from its father, and this is the red ones that it got from its mother. So it would make sperm, and this particular sperm would have all of dad's traits that he got from the father would be passed on to the offspring. But these could easily just randomly line up this way. And so this is how we get all of these different combinations of gametes, right? So we go back and say this is like this. And so whenever these separate in meiosis 2, then we get a gamete that looks... Here, let me finish drawing this other gamete. I got red. So this one would be, this particular one, I'm going to fill it in. So this particular gamete here would be all moms, right? But it lined up this way, which is this is just flipped, and this could happen. So this is a different event. And in this case, the gamete, I just colored over that. Oops. I don't know when I'm switching colors. I got the same color there. So this would be one gamete, and this would be another. So these are different from these two. And because of this alignment on the metaphase plate during meiosis, and it's random, right? 50-50 in any order, then you can have all of these variations in gamete production. Okay, so let's see. I think that's the end of this lecture. So that's the end of everything that we're going to cover on the exam. There's one thing that I wanted to go over real quick, and that is this pedigree analysis. So there are some questions on the quiz and on the exam on this and on the problem set. And so I just want to make sure everybody understands this. So it's pretty straightforward. All you're doing is you're calculating the probabilities of a particular outcome. And we're using the rules of multiplication because they're independent of one another. So this is saying PKU. We know PKU is a recessive trait, so we can just use little a. We don't have to use the actual nomenclature here. And so we're going to say this individual who doesn't have it, because PKU is very rare, we're going to always assume that anyone marrying into a family that has a trait or has a disease or is a carrier is going to be homozygous dominant. And so if this occurs, then we would assume that all of the offspring here are going to be heterozygous, right? Just like in normal parental, and then this is an F1 generation, right? So if we're trying to calculate the probability that this child of these two parents is going to have PKU, we have to look at the pedigree to figure that out. And so this one's easy, right? It's 100%. It's 1, right? So when you multiply 1 by anything, it's going to be 1. Now we got to figure out what's the probability that this offspring, or in this case, we want to know this offspring, but they're all the same, right? So what is the probability that this offspring here, this B, is going to be a carrier, right? It can't have PKU or will be filled in, right? And so if these, I don't know why I put that, we would assume that this person is going to be homozygous dominant, right? Because they're marrying into a family that has this very rare allele. So what's the probability that this person would be a carrier? And so we do a Punnett square, right? It's pretty straightforward. We have big A for this parent, big A right here. And then for this parent, we have big A and little a. So we can do out the Punnett square, and you can see that the probability that they're going to be a carrier is 1/2. And so now let's take the other family line. So we have these two parents. We know that one of their offspring has PKU. So this offspring has to be little a, little a. And the only way to get that is if both these parents are heterozygous. So we know that for a fact. And so now we want to know what the probability that this person is a carrier. So we have two heterozygous individuals. And so the probability is again, remember whenever we did it's fatal or whatever, when we did the crosses, and we could eliminate that possible outcome because it was embryonic lethal. This is not possible, right? Because we know this person is not filled in. So the probability they're a carrier is 2 out of 3, right? Not 2 out of 4, because this we have to eliminate this little a possibility because this isn't filled in. So this probability is 1/2. This is 2/3. Now, if the only way that you get this child that to be little a is if these are both carriers. So the probability of the A individual being a carrier is 2/3. The probability of the B individual being a carrier is 1/2. Now, if they're both carriers, what's the probability that their offspring is going to get PKU? And again, it's just standard Mendelian genetics. The probability, if they're both carriers, of any one of their offspring having PKU as an independent event is 1/4. So the question mark is 1/4. Now we have to multiply all of these together because they're independent events. So we have 2/3 times 1/2 times 1/4, which gives us, oh, I don't know why it's not drawing over there, but it's not. So that gives us 2 times 1 is 2, and then 3 times 2 is 6, times 4 is 24. So the probability is 1 out of 12. And let me just do the math real quick. So that is 0.083 repeating, or roughly 8%. Probability that this offspring, based on this pedigree, they would have a child that has PKU. So I just wanted to go over that so that you guys would know how to solve that problem. All right, so that's the end of the first exam lectures, and then I'll make a recording probably later on this week, maybe Thursday, for the second exam. If you guys have any questions, let me know. Again, I have my standard office hours are back because I'm back from my conference. So send me an email or show up to office hours if you have any questions. You just read the announcements. All right.